Okay, hello everybody. I just arrived by train because the NS hopefully screwed up today. I lost about 1.5 hours in the train and I had a meeting this morning so I couldn't come out earlier. But anyway, I'm here, so I'm going to talk to you about the embedded AI for computer vision and biometrics. All kinds of things that we do in our lab. So I'm from the University of Twente, from the Data Management and Biometrics group. And I lead a subgroup there about computer vision and biometrics. So I came from this faraway place, and it took a very long time. So yes, Twente is there, and now we know that it's very far away if you come by train. The University of Twente, I don't know if you know the University of Twente. It was founded in 1961. It has 5 faculties and about 12,000 students in 2024. Then 35% of the students are international, so quite a large portion of that. And in 2024, we had 237 PhD students and a bit over 4,000 staff members. I don't know exactly the ratio of the scientific staff, but that's more or less it. This is a picture of my group, I think about a year ago, the Data Management and Biometrics group. And yeah, so as I said, the subgroup Computer Vision and Biometrics is about half of the group, I would say. 7 scientific staff members are involved in this type of research. At this moment, we have about 10 PhD students, 4 new ones upcoming, by the way, some guests, and about 15 to 20 master students a year. And we are very diverse. We have, I counted once, I'm not sure what the status is right now, but I counted 12 different nationalities in our group. Now, what kind of things do we do? If you look at our research topics, for example, we do vascular biometrics. We recognize people by their vascular structure in the fingers, for example. We do face recognition in all kinds of sorts and forms, 2D, 3D face recognition, so the shape of the face, but also face recognition from large distances, and for example, from profile, etc. Then we also do in things like action and behavior recognition. We do for the police and ministries things like evaluation of biometric systems. So how well are they operating in reality? So you deploy these systems, for example, at Schiphol, but you have to know how well they work in reality. Of course, the vendors always say they are very good, but can we trust them? So we do research like that. A relatively new line of research for the last something like 6-7 years is image manipulation detection. Of course, you're all aware of deepfakes, etc. We have a new project where we try to contribute to detecting deepfakes, but also all kinds of other image manipulations. We do forensic biometrics. If you want to use biometrics, automated systems for human recognition, and want to have some kind of evidence in a court case, you have to formulate this, you have to present this in such a way that a judge can do something with that. And that's not straightforward. Then, of course, we work on embedded AI solutions as well. That's why I'm here, right? And other things like robust explainable AI and computer vision. And there's some very funny things as well. For example, flower recognition, but also recognition of Roman emperors, statues of Roman emperors, which is after all also something like biometrics, right? And we also did cow recognition, red expression recognition, red face expression recognition, amazing. So some running projects, the top 3 are European projects, image manipulation, I mentioned it before, mobile biometrics at the border, but also all kinds of inspections on trains and railways, etc. And then, of course, the very important thing here is the embedded AI lab that we have, and some other stuff, robust vision. So we have a quite wide area of interest. I will skip this part about our master's specialization, where we offer a bunch of courses in computer vision and biometrics, and go straight forward to the embedded solutions that we develop in our labs. what I see as embedded, and there may be multiple definitions of what is embedded, of course, is that you have a system that is not dependent on cloud or other servers. So you have basically a standalone system. Of course, it can still communicate with the cloud, but it's not necessarily dependent on it. So that is a thing that I would see as embedded. Furthermore, embedded systems are normally characterized by limited resources. And limited resources can mean everything. It can mean like almost nothing to quite sizable. So all of these solutions can be embedded, and I will show some variations of what we use in embedded solutions. Another characteristic is that they have modest power consumption. And again, modest power consumption can mean anything. It can be 1 microwatt in some cases. That could be the limit. But it can also be that you have a reasonably sized computer with a battery, for example, that can deliver far more power. So you have a range. But anyway, so you have more or less standalone systems. Now, about the challenges for computer vision and biometrics, these are systems, solutions that normally require a lot of computing power. Because, yes, they are complicated problems. You have large amounts of data. If you have images, you have a lot of data. If you have videos, you have even more data. So normally, you have quite a lot of data available, and you have to do lots of processing. And the evaluation, the inclusion of AI, of course, doesn't make things easier. You have millions of parameters to deal with, so it even needs more resources. So the real challenge is here to use AI, but in a modest form that still is performant. Now, I will show you some things that we do. So practical system implementations that we worked on mostly with students, in all these cases, in almost all these cases, we address the hardware, the sensor side as well, so we build sensors as well. And of course the software implementation of these solutions, AI solutions. By the way, the AI solutions that I will be talking about will not only be deep learning, because you also have other types of AI that may be more conventional, but I think they're still kind of AI because they are still artificial intelligence. And I also will talk a little bit about theoretic concepts. So, to start right away with the first example, I mentioned finger vein recognition already. So we built and we're working on developing sensors and systems for finger vein recognition. Now, if you look at your finger, you probably will not see any veins there. Please have a look. I see some people look at the fingers. Some people with very thin skin can see veins there. But if you use near-infrared light and you shine it through the finger, the hemoglobin in the blood will absorb the near-infrared light more than the other tissues in your fingers, and that means that you can see dark lines projected against a lighter, brighter background. Something like over here. You can also see that the veins are not super sharp, but you can see there are patterns. And the interesting thing about these patterns is that they're unique for every person and every finger. So that means we can identify the people by using these finger vein patterns. Now, to record an image like this, of course, you have to build a device. Now, so we have various versions of devices that we built, mostly by students, bachelor and master students worked on these things. And you need a near-infrared light source. So you can see here some near-infrared light LEDs. You need a camera over here that is sensitive to the near-infrared light. And it's hidden in this box over here. And you have to place your finger over there. In this setup, we also have a nice display that shows the finger real time. And so we can record the finger vein images. Now, the next thing, of course, is use these images to recognize people. So you have to compare two of these and decide if the two images are of the same finger. So the implementation that we have right now on this embedded system is based on a Raspberry Pi that is built in here. So quite limited resources that we have, and it's mostly conventional. So there's a part that does the finger detection. It finds out which part of the image is the finger. It does vein extraction, and this is actually quite classical. So it's just looking at gradients over here, but in a clever way, because you have very unsharp images and pretty noisy as well. And then basically the patterns that you extract, you compare using normalized cross correlation. So it's a very straightforward approach. And this approach has been published by a guy called Miura quite some time ago already. So as I said before, this whole system, we have various versions of this system, has been developed by master students and bachelor students. We also have a deep learning based method that has been developed by a PhD student of mine, and it is actually quite suitable for implementation on a small resources platform. So that will be the next step for this whole thing. If we have the image quality properly under control for these systems, then we also implement this on the Raspberry Pi, so we will have a deep learning approach. And this deep learning approach actually performs somewhat better than this Miura approach. So that was number one. But we have several other things that we worked on and on embedded platforms. This here is a hand grip sensor. And what can you use this hand grip sensor for? You can check if people hold things in the proper way. For example, people suffering from hand diseases, rheumatic diseases, for example, they so often do not know how to hold things because they are afraid that they will hurt their hands. They're afraid that they will squeeze things or maybe drop things if they do not hold them properly. So with this sensor, we have a very high resolution imaging sensor that measures the pressure used or the grip used in your hand, as you can see over here. And you can also see in the images here that you, with the colors, you can image this. Now, what is nice in this is that you can use these images first for diagnosis. You can see if people do it the correct way. The second thing is, because you have immediate feedback, you can also instruct people. You can say, okay, pay attention that the pressure of your hand is more equally divided over the whole thing. So it's a very useful device. We built those sensors, developed those sensors ourselves, as you can see over here. And the platform that we used in this case was a Raspberry Pi Zero, and this was all built in a setup like this, all in one thing, including battery and the Raspberry Pi Zero. And if you then put your hand on the sensor, then you get an image like this. So you see the fingers over here. I think the thumb is just outside the image in this case, and the palm of the hand as well over here. Let's see. Yeah, so I will move to the next example. Next example is together with a bunch of students, we have been competing in the so-called RDW, which is the Dutch Vehicle Authority, self-driving challenge. And the idea is to build a car with some sensors and to let it drive autonomously over a track, detecting traffic signs, etc., and also do what is on the traffic sign. So if you see a traffic light with a red traffic light, you have to stop. If it's green, you have to continue. You have to detect traffic signs, etc. And you might say, okay, yes, but I have this in my Tesla as well, or in my Kia, for example. That may be true, but still it is very interesting to investigate how these systems actually behave, because that is a big question mark. Yeah. Probably if you have these systems, you also observe that it's not always operating as expected. And for RDW, this is very useful information. And that's why they organize this, to get a better grip on how these systems can fail. And they do fail, trust me. But you can see here the little car that we built with 3 cameras on it. In principle, there's also a LiDAR, but I don't think it's mounted at this moment. It has a so-called CAN bus, which is officially the same kind of CAN bus that is in those advanced cars, those advanced electric cars. And it does things like lane detection, so it detects the side of the lanes, the lines here. 2 minutes, I have to speed up. And again, it's developed by master's and bachelor students, and they drove on the track, stopped where they had to stop, and they also adapted the speed, and they stayed on the track most of the time. Last example that I have is iris recognition. So again, a box was built, and you need near-infrared to record the iris, and the iris is this part of the eye, and it has tiny muscles there that are also, again, unique to people. And of course, you all know iris recognition. Well, you need several steps to do that. You need segmentation of the iris, then it's rolled out into a production like this, and I won't go into details because I don't have time, of course. Again, we made an implementation on the Raspberry Pi, and it is a combination, a hybrid thing between deep learning stuff and conventional stuff. So deep learning, the segmentation is deep learning. It turned out that it's much more reliable than using conventional segmentation, but the rest of the processing is mostly more traditional. I'm almost at the end. The last bit is the work of a PhD candidate of mine. He's here as well. He already had a short presentation today. So it's Sebastian Bunda, and he's looking at squeezing deep learning models onto very modest hardware. So that includes things like reducing the size using quantization and other approaches, but also adapting the model to specific hardware. For example, you have an FPGA and it can't do anything, it can't do everything, so you have to choose how to implement things, and the neural processing units as well. And the network architecture searches is the current focus of his work, where you get images like this, for example, where you have an accuracy of a system versus the number of parameters, and you're trying to find a system that has as low number of parameters as possible, but on the other hand, as high accuracy as possible. And you can see here that if you go below a certain number of parameters, you cannot guarantee the performance anymore, so you try to find the ideal spot over here. And he's working on things like that. That's more or less it.
Thank you very much. So I don't think